Okay, so for part one, we first started with deriving the transfer function. So basically, for the low-pass filter circuit, I did KCL at two nodes, node VA and node VB. So I calculated the current through this resistor and this resistor, and then through the capacitor here. So we did KCL for every resistor, two resistors and one capacitor here. Then we done all of this, and finally got V out over Vs, which is the output over the input, and gave us this transfer function. Then using the transfer function, we can get the angular frequency, which is omega, by this relation. So omega 1 is equal to this one, omega 2 is equal to this one, even though R1 is equal to R2 in this low-pass filter. And then, just to make sure that the calculation is correct, I calculated the value of the angular frequency here. Then I used the values of the frequency, which was 2K, and Q, which was 0.0707, to get R, C1, and C2. So using these calculations, which was very tough for me, then I derived this equation. I'm gonna rewrite it because it seems like a mess, but I'm gonna just demonstrate it real quick. So here we have R C1 squared is equal to this number, which will allow us to get R1 and R2 because they are similar. And so we get R1. After we get R1, we can calculate C1 and C2. And the most important thing is that C1 is equal to 2C2. So now we can put all of this in OrCAD. So this is our original low-pass filter circuit, and this is the optimized low-pass filter circuit, and these are the new values that I calculated. So now after we run a simulation in PSpice, we get our original circuit curve here, and then the optimized one shown in the right here. So original, then the optimized, and this is for the low-pass filter. And last thing, we build the circuit for the low-pass filter to get the sine wave. So we plugged it to the AC power source and plugged it to the oscilloscope to, yep, we can press stop to get our sine wave, and we can auto scale it and play with it to get the correct sine wave. So this is basically the low-pass filter part. Okay, so for my second part, which is doing the bandstop filter, first of all, starting with the transfer function and the circuit, I created three nodes, A, B, and C here. So using KCL at node A, we get the current here. Then, so I basically started from here, then here, so A, node A, node B, node A, node C, then node B. So all the way around. So node A first, then node C, and then node B. And all of these calculations, then we derived the main, or they derived the transfer function here. Okay, then after that, I did the ORCAD simulation here. So this is the ORCAD circuit, and if we run the simulation, we get this shape, which is the V shape, which is very similar to this one, which is the expected simulation result. Then after that, I built the circuit here using 3 amplifiers, which is basically the same as the ORCAD circuit. 3 amplifiers with 5 resistors and 2 capacitors with an AC power source. Okay, so we have 3 amplifiers, 5 resistors, and 2 capacitors. Then we plugged in the input here to this one, the AC power source, and the input also goes to here. And for the output is this one, which is plugged into one of the amplifiers, which is basically here. Okay, so this is the same line, so it's either this one or this one. And we got this sine wave, which is basically showing us the V shape, just like the given simulation result. And this is for the band stop filter. And for the band pass filter, we basically created 2 high pass filters and 2 low pass filters. So this is basically the high pass filter circuit, low pass filter. I connected all of them, and we messed and changed the values of the capacitors, the outside capacitors and the outside resistors. Then we ran a simulation and got our final result. So this is basically shows the low pass filter, the high pass filter, and the relation between them. And yeah, I think that's it.